So, good afternoon to everyone. I welcome all of you to the 66th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Professor Boris Malomed. Professor Malomed is a well-known name in nonlinear physics community. In view of students, I will read out his achievements in a very brief manner. Professor Malomed completed his PhD in theoretical physics in the year 1981 and obtained BSc in theoretical and mathematical physics at the Institute for Theoretical Physics of the Ukrainian Academy of Sciences, Kyiv, in the year 1989. After working almost 10 years in Moscow and France, he moved to Tel Aviv University, Israel, in the year 1991. Since then, he is working there at various capacities. Under his guidance, several students obtained their PhD, and he had acted as mentor for several postdoctoral fellows as well. He is serving as editorial board member in several journals. He is acting as a referee in all well-known journals which covers the area of research nonlinear dynamics. This includes PRL, PRA, PRB, PRE, EPL, Optics Letters, Optics Express, Optica, Journal of Physics A, B, JOSA B, Optics Communications, Physica D, and so on. In fact, I have mentioned only a few journals. He has scientific collaborations worldwide and visited several countries. His H index in Google Scholar is 96. He has a very high H index and citations are about to reach 50,000. He is also serving as a referee for scientific foundations and in appointment committees throughout the world. If I read his CV, it will take another 1 hour. Since I don't want to take much of his time now, I hand over the session to him. Over to you, Professor.
Okay, thank you very much for your introduction. And of course, good afternoon to all participants. And I would like to thank the organizers for the invitation to give a talk at this very interesting series of lectures. So here you can see the title of this talk. And let me start from some introduction to mention a couple of things which are definitely known to everyone who is listening to me now. So this is about the concept of solitons. So solitons are solitary waves. These are localized objects which have been predicted theoretically and discovered experimentally in a very broad class of physical systems and settings, and they are supported, as is commonly known, by the stable balance between the nonlinear self-attraction of the wave field, or in terms of optics, it's maybe called self-focusing, and on the other hand, there is a linear part of the model which tries to stretch the field, so which acts in the opposite direction. It's a linear dispersion or diffraction. So as a result of the stable balance between the nonlinear self-attraction and linear dispersion or diffraction, that is self-stretching of the field, in many cases, stable localized states appear. So arguably, the most important equation which gives rise to solitons is this celebrated nonlinear Schrödinger equation, which is written here. This equation appears in a great number of physical realizations, as it is, first of all, considered in the one-dimensional form. So this is the equation for the complex wave function psi, and we have the single coordinate x and time or evolution variable t. This nonlinear term gives rise to the self-attraction of the field. And then as an elementary fact is that one can immediately find a family of exact soliton solutions in this form. Now, a remarkable property of this equation is its exact integrability by means of the inverse scattering transform. So the exact integrability actually of two equations. There may be the nonlinear Schrödinger equation with a sign minus that we are going to consider, and also with a sign plus with the opposite sign, and the opposite sign of the nonlinearity, where bright solitons do not exist, but still both equations are exactly integrable by means of the inverse scattering transform. And this fundamentally important fact had been discovered in the classical work by Zakharov and Shabbat in 1971. And the fact that the equation is exactly integrable gives rise to the huge number of non-trivial exact solutions. So those fundamental solitons which I mentioned are elementary solutions. The existence of fundamental solitons does not require integrability. However, the integrability gives rise to highly non-trivial exact solutions for such states as collisions between solitons. They collide completely elastically, essentially passing through each other, or also for bound states of two or several solitons. So exact solutions for bound states when the solitons actually are placed at the same position, they exist in the form of the so-called breathers. Breathers are such nonlinear superpositions of several fundamental solitons which perform a periodic variation in time. Now, these solitons have been experimentally observed in some very famous works, in particular, soon after the discovery of the exact integrability of the one-dimensional nonlinear Schrödinger equation. Hasegawa and Tappert in 1973 were able to derive this equation as an approximation from the system of Maxwell's equations, which govern the propagation of electromagnetic waves, that is, optical waves, in a nonlinear optical fiber. So they predicted the possibility to create such a soliton in optical fibers, and indeed they were experimentally discovered 7 years later in this famous experimental work by Malinauer, Stoll, and Gordon. So this is essentially the illustration of their famous results. When the power of the light pulse is low, it just suffers the linear stretching under the action of the dispersion. However, when the power attains a necessary level, then the nonlinearity becomes essential, and this input forms a stable soliton. And then, moreover, when the power is still larger, the input can give rise to multi-soliton states. In particular, these pictures, they essentially represent the experimental observation of the 2 and 3 soliton states in the optical fiber. Then, another very famous experimental application of the integrable nonlinear Schrödinger equation, in that case, it's frequently called the Gross-Petaevsky equation, is to Bose-Einstein condensates, that is, to ultra-cold bosonic gases of bosonic atoms. So the system can be made effectively one-dimensional in the so-called Seeger-shaped trap, when the gas is very strongly confined in 2 transverse directions, but is quasi-free in the 3rd direction. So it's effectively a quasi-one-dimensional setting. And it was predicted that actually the effective equation in the mean field approximation will also be equivalent to the nonlinear Schrödinger equation. With its natural sign of the nonlinearity actually would be self-repulsion. But nevertheless, there is a experimental tool which can be easily used, for example, in the condensate of lithium-7 atoms, and this is called the Feshbach resonance. Feshbach resonance makes it possible to effectively switch the sign of the interaction from repulsion to attraction, and this way it can actually open the way, open the road for the creation of solitons. And indeed, experimentally, such solitons were reported simultaneously in these 2 famous experimental works. One by the group of Hewlett at the Rice University in Houston, and simultaneously by the group of Solomon in Paris. In particular, this is a famous experimental picture an image taken by the group of Hewlett, which shows the cluster. They were able to create any number of solitons from 1, roughly speaking, to 7. So this is a cluster of 7 solitons of different amplitudes, which they were able to create in their famous experiment. So this is essentially the distribution of the density of the gas, and each peak represents an individual soliton. Now, the subject of this talk is to an attempt to create multidimensional solitons, not one-dimensionals, but 2 or 3-dimensional solitons. The models which give rise to 2 or 3-dimensional solitons are quite similar to the one-dimensional models. So this will be, first of all, again, the nonlinear Schrödinger equation, which should be written in the 2 or 3-dimensional form. Of course, we will see this equation, but when we proceed from 1 dimension to 2 or 3 dimensions, there appears a fundamental difficulty. The difficulty is the stability. Roughly speaking, in 1 dimension, nonlinear equations which produce solitons produce stable solitons most typically. For example, all solitons of the 1-dimensional nonlinear Schrödinger equations are completely stable. However, this is not so if we just try to construct solitons for the 2 and 3-dimensional versions of the same equation. Exactly the same equation, like the nonlinear Schrödinger equation with the cubic nonlinearity, if it is written in the 2 or 3-dimensional form, immediately it can give rise to formal soliton solutions, but these solutions are unstable for the reason that exactly the same equation gives rise to a new physical phenomenon, which is called a collapse. Collapse, or in other words, this is a catastrophic self-compression of the wave field. So in the 2 or 3-dimensional cases, the equilibrium between the nonlinear self-attraction and linear dispersion or diffraction is not stable. And as a matter of fact, the self-attraction becomes a dominant factor, and eventually it leads to creation of the infinite, of the singularity in terms of this mathematical equation. So after finite evolution time, the solution will develop an infinite density, singularity at some point. So as an example of that, we can just look at the 2-dimensional nonlinear Schrödinger equation. It's, formally speaking, just a very straightforward extension of the 1-dimensional equation to 2 dimensions. And then formally speaking, so one should, of course, note that when we replace the 1-dimensional nonlinear Schrödinger equation by the 2-dimensional or 3-dimensional equation, we lose the property of the exact integrability. We no longer can find exact analytical solutions. Even for the single soliton, it's not possible to find it in the exact analytical form. By itself, this is just a technical problem because soliton solutions in 2 and 3 dimensions still exist, and then can be quite easily found numerically, or analytically they can be found in the approximate form by means of what is called the variational approximation. So if we want to construct a general soliton solutions of this equation in the 2-dimensional space, we can look for a solution which will have, in principle, the embedded vorticity, the topological charge. So the ansatz, which we can substitute in this equation, is written in this form. So mu is just a negative constant factor, which is called the chemical potential. S is, so it's written in terms of the polar coordinates, r and theta. So S is the integer. Obviously, we can write this term in the phase. Theta is the angular coordinate. And S is called either a topological charge or simply vorticity. It's also maybe called the winding number. So we can expect that if S is equal to 0, this is a fundamental soliton with 0 vorticity. And in principle, such solitons exist for any integer value of S, positive or negative. So mathematically speaking, what we should do, this is a solution of a relatively simple exercise. If you substitute the ansatz in the equation, then the equation becomes exactly equivalent to this radial ordinary differential equation for the real function US. And then, of course, it's quite easy to solve it numerically and produce a localized solution. Actually, we can produce a family of solutions because such a solution can be found for any negative value of the chemical potential. So this is a typical 2-dimensional view of such a soliton. So what is shown here is a distribution of the local density produced by the numerical solution, this time for the zero vorticity, for the fundamental solid two-dimensional soliton. Such a soliton is usually called the town soliton because for the first time they were numerically found in this famous work by 3 people, and the last author, Towns, was a very famous physicist working in nonlinear optics, and because of his name, such solitons are usually called town solitons. And it's actually interesting to mention that they published their paper when the word soliton did not exist, because the word soliton was coined a year later, 1965, in another famous paper by Kraskal and Zabusky, which actually considered a completely different model, a one-dimensional Korteweg-de Vries equation. So in that, when this paper was published, word soliton did not exist. Therefore, this solution was found in terms of optics just a one-dimensional self-trapped, not one-dimensional, simply self-trapped beam of light. Okay, so historically, this is the first soliton which was ever predicted in optics, but it has never been experimentally observed, unlike other optical solitons which were predicted later. And the reason is that it's completely unstable. So before that, before discussing its instability, we can also look at the similar solitons, but with embedded vorticity S. In particular, this is a radial cross section of the similar soliton. But when we have the vorticity 1, in that case, we have the hole in the center. It's roughly speaking similar to the asymptotic structure of the Bessel function when the argument is approaching 0. And now, such a soliton can be quite naturally characterized by its norm. So the norm is a straightforward expression, which we can calculate numerically if we know the solution. And then one can very easily find that this two-dimensional equation with the cubic nonlinearity has a specific property of the conformal or scaling symmetry, scaling invariance. And then it's very easy to prove analytically that although we have a continuous family of solutions, which any negative value of mu gives rise to its own soliton, but nevertheless, if we consider solitons with the same value of the vorticity, for example, with vorticity 0, in the case of the town solitons, all solitons which belong to this family, they have exactly the same value of the norm. So in that sense, they are degenerate solutions. They are also degenerate in terms of their energy. It's possible to prove that if we write the Hamiltonian of this equation, and then we consider the value of the Hamiltonian for the family of solitons, exactly all of them have the energy or value of the Hamiltonian, which is exactly equal to 0. And this universal value of the norm for all town solitons with 0 vorticity, it can be easily found numerically, and this is its value. Also, if we fix any integer value, non-zero integer value of the vorticity, again we will have the infinite family of solitons with exactly the same norm. Of course, the norm, this fixed norm depends on the vorticity. In particular, it can be found numerically, but it also can be approximated analytically in a rather accurate form by this simple formula. Now, about the instability. Okay, about the instability. So we can look at the town soliton for simplicity just with 0 vorticity. And then the analysis demonstrates that it is unstable against small perturbations. So this is a result of the direct numerical simulation of the evolution of this equation. So what is shown is the evolution of its radial structure, radial profile. Because in the course of the evolution, this soliton remains axially symmetric. And originally it seems to be stable, but gradually the small instability starts to grow, and then its growth quickly accelerates, and eventually, after a finite evolution time, this soliton is going to develop a singularity, a solution with an infinitely large value of the amplitude at the centers. So this is what is called collapse, and therefore the town solitons are completely unstable. So one can actually say that the town soliton is a separatrix, which is a border between two different types of dynamical behaviors. On the one, so because it has this fixed value of the norm and not. So if any value of, if we take any input with the norm exceeding this particular value, it will develop the collapse. And so it will destroy by the collapse, by the implosion, or by the blow up. On the other hand, if we take any input with a value smaller than the collapse, then it will not be able to develop the collapse, but it will simply decay. So the town soliton is a separatrix between these two different types of behavior, between collapsing solutions with a norm exceeding this critical value and decaying solutions whose norm falls below the critical value. And then, as it's commonly known from the theory of dynamical systems, any stationary separatrix solution, of course, is dynamically unstable, because if we add the small perturbations, we will push the evolution either towards the collapse or towards the decay. Now, this actually, so the fundamental problem, which is physically very interesting, is to somehow modify this equation and propose a physically relevant model which would make it possible to create stable multidimensional solitons. And one general possibility is suggested by this consideration, because if we will be able to somehow modify the nonlinear Schrödinger equation in 2 dimensions, so that we will be able to create a soliton whose norm is smaller than this critical value, smaller than n naught, it will not be able to develop the collapse. And then actually it will have nothing to do but to become stable. So we will see that indeed there is a possibility to stabilize the soliton by means of this mechanism. Now, in the 3-dimensional case, the nonlinear Schrödinger equation is also a physically relevant object. As well as in 2 dimensions, it's relevant both for nonlinear optics and for Bose-Einstein condensates. But the situation with the stability is still more difficult, because in the 3-dimensional case, the collapse is supercritical. Supercritical means that, formally speaking, this critical value of the norm, which is necessary to initiate the collapse, is equal to 0, which means that in 3 dimensions, any input, even with an arbitrarily small norm, is able to start the spontaneous evolution towards the formation of the singularity. Therefore, stabilization of solitons as a 3-dimensional case is still a more challenging problem. And then another essential aspect is that if we consider solitons with vorticity in the same model, in the 2-dimensional nonlinear Schrödinger equation with the cubic nonlinearity, they are even more unstable, because even before they are going to develop the collapse, if we look at the structure of the soliton with embedded vorticity, this vortex ring, it will be unstable, first of all, against spontaneous splitting into fragments. For example, this is a spontaneous splitting of the vortex soliton with vorticity 1, and this is a similar result with vorticity 2. So here it spontaneously splits, roughly speaking, in 2 fundamental solitons with 0 vorticity. Here it splits into 4 solitons, and later each secondary soliton will be destroyed by the intrinsic collapse. Okay, so this general topic of predicting and experimentally observing stable multidimensional solitons has attracted much interest, and there are some reviews on this topic. First of all, there is a relatively short review available here in the general form. Then there is a more specific review which analyzed stabilization of multidimensional solitons with embedded vorticity, or vortex solitons. Then there is another topic, is stabilization of multidimensional solitons in dissipative systems, in dissipative models, where there are possibilities to predict stable dissipative solitons, but all the analysis is completely different. Also, there is still another possibility, which is it's actually easier to predict stable multidimensional solitons in models with non-local nonlinearity. So there are some review papers on this topic too, and eventually there is a new book which I recently published, just actually a month ago, essentially. And this new books summarizes all these results, both for conservative and dissipative models, and also for non-local models in a systematic form. And now, as concerns the remaining part of the talk, it may be naturally structured against, according to the attempts to solve the most important problem, stabilization of the multidimensional solitons, because the instability is a really severe problem for them. So according to these different possibilities to stabilize them, we can actually consider three topics. First of all, in the brief form, we can consider a relatively old approach. This approach is based on considering the nonlinear Schrödinger equation with the competition of two different nonlinearities, self-attractive cubic and self-repulsive quintic nonlinearity, higher order nonlinearity. Of course, higher order self-attraction will definitely prevent the collapse, and therefore it can provide the way to stabilize multidimensional solitons. Then a relatively new topic is it actually makes it possible to stabilize solitons in the two-dimensional case, even in the three-dimensional case, when we have just the traditional cubic nonlinearity, self-attractive cubic nonlinearity, nothing else. But in that case, we will actually consider a system of two coupled nonlinear Schrödinger equations. The coupling will be just represented by the specific linear terms, which represents the so-called spin-orbit coupling. And this system of two cubic nonlinear Schrödinger equations with a specific linear coupling between them will be sufficient to provide full stabilization of the solitons. And then the latest topic, which I will try at least to briefly consider, is quite interesting because it's not only the theoretical prediction, but also the direct experimental realization of the stabilization of essentially soliton-like objects in the 2- and 3-dimensional geometry. And this is creation of the so-called quantum droplets in the Bose-Einstein condensates. So they can be stabilized by means of a specific mechanism, which more or less, mathematically speaking, also amounts to the addition of the higher order self-repulsive nonlinearity, not quintic, but quartic. We will discuss what it means. And it is induced by the effect of quantum fluctuations. Okay.
Question.
Now let's, yes.
Can I ask a question?
Yes, yes.
Yeah. So you use the term vortex soliton. To me,
yes.
Vortex means something rotating, right? So yeah. So is there anything which is rotating? So perhaps I did not get that physical insight.
Okay. So what happens is that in the stationary form, nothing is rotating because the vorticity, for example, if you look at this stationary form of this vortex soliton, nothing is rotating, is a stationary solution, and the vorticity is represented by the phase structure. The point is that if you will perform a round trip here, then you will see that as a result of the round trip, you will have the change of the phase by 2 pi. So this phase change by 2 pi represents the, so to say, hidden vorticity. So hidden because it does not show it does not show any explicit rotation. Now, if this is the case when it is unstable and it splits, for example, into the set of fragments, it depends on the particular instability mechanisms. In some cases, actually not exactly here, but in some cases, when they split into fragments, these fragments may, at least at the initial stage of the splitting, they can indeed demonstrate the trend to a circular motion.
Okay, thank you.
Mm-hmm. Okay, so let's get back to this where we stopped. Okay. Right. So now, first of all, we will look at this possibility, which was elaborated relatively long ago, and this possibility is represented. We can write this in the 3-dimensional form which is the most interesting situation. So here, this is a three-dimensional nonlinear Schrodinger equation. The notation here is adopted from optics. From optics, it means the evolutional variable is not called time, it's called z. Z is a propagation distance, because in optics, the natural formulation is that is one which in which one should predict the evolution of the input along the propagation distance, while the temporal variable tau essentially becomes, formally speaking, as an additional coordinate. But it's actually this difference in the physical meaning of the variables does not make it a real difference in the interpretation of the results. So what is essential here, it's assumed that in addition to the cubic self-focusing or self-attraction, we also have quintic, this term, self-defocusing, self-repulsion. So this is not just a purely theoretical speculation, because it's known that there are some optical media in which the nonlinear response to the optical signal can be indeed approximated with a reasonable accuracy by the combination of these two terms. Then, if we want to find a soliton solution, let's say in the 3 dimensions, we can introduce cylindrical coordinates. In the cylindrical coordinates, we can, if we want to have the soliton again with embedded vorticity, we can look for it in this form. Again, this is, so in the cylindrical coordinates, this is again the angular coordinates. We can assume that we have some integer vorticity s. If s is equal to 0, we have the fundamental soliton. It will be a spherically symmetric, a spherically isotropic solution. Otherwise, if we have non-zero s, the symmetry is reduced from spherical to cylindrical. And so in the general case, if you want to find such a solution, we will have to solve this stationary partial differential equations with in the radial coordinates with radial variable r, and this is actually the axial variable tau, which plays a role of the third coordinate in the cylindrical system of coordinates. And then it's necessary to numerically solve this equation for positive k. Positive, this is the propagation constant. And previously I mentioned that this similar constant had to be negative, because by definition in optics, this constant is introduced with the opposite sign. In BEC, it's usually written as minus mu. In optics, by tradition, it's written as plus k. K is called the propagation constant, or simply wave number. And then actually, we can also consider the two-dimensional version of this cubic quintic equation. In two-dimensional version, we simply drop this term. Okay, so the first essential theoretical result was predicted long ago. It was predicted in first in 1997. More than, roughly speaking, 25 years ago, by means of numerical simulations by people from Spain, Quiroga Tejero and Michinel. So what they did, they ran direct simulations of the two-dimensional version of this equation. And this was a very important fact that they found. The fact that actually this equation in 2 or 3 dimensions will make it possible to create stable fundamental solitons with zero vorticity is obvious. Why it's obvious? Because if we have this higher order quintic term, which is self-repulsive, obviously it will prevent the creation of the singularity, because singularity means that the local value of the intensity must become very large. But if it is very large, this term will become dominant. It actually definitely arrests the development of the singularity. Therefore, it will stabilize the fundamental soliton. So the stability of fundamental solitons here is almost a trivial fact. What is quite non-trivial, even in 2 dimensions, is the possibility to create stable solitons with embedded vorticity. This is a real issue. And so this work, these people for the first time, more or less empirically, just by means of direct numerical experiments with this equation, they were able to find examples of such stable vortex solitons in this model. And then a more rigorous mathematical analysis, also essentially, it's not an analytical result, it was also based on the numerical calculations, but performed in the rigorous mathematical framework. It was reported by Pego and Worchel. And so what they observed in their results can be summarized as follows. This is radial profiles of solitons with embedded vorticity. So here are shown 5 examples with values of this vorticity, or in other words, binding number, topological charge 1, 2, 3, 4, 5. So what happens, the result of the stability analysis demonstrates, as we make this soliton, roughly speaking, fatter and fatter, if we try to increase its norm, the point is that it easily follows from the equation that the local amplitude of the solution cannot exceed this maximum value, because the competition between cubic self-repulsion and cubic self-attraction and quintic self-repulsion does not allow the solution to develop the value of the amplitude which exceeds this maximum value. So nevertheless, we can create a soliton with a very large value of the norm, but it means that we should make it very broad. So in a sense, very fat. And then the result is that the soliton becomes stable when it's fat enough, when it's sufficient, when its norm is sufficiently large. In other words, when its size, radial size, is large enough. So what is shown here is this the shape of the soliton at the stability border. If the soliton is broader, wider than shown here, it will be stable. If it is more narrow, it still exists as a stationary solution, but it will be unstable against splitting. So the soliton with topological charge 1 is stable when it's still relatively not very fat, but then when we increase the value of the vorticity, we can, in principle, for any value of the vorticity, we may find some family of stable solitons, but they should be extremely fat. For example, this is for n equal to 5. And these are some direct simulations from the original paper by Quiroga, Tejero, and Michinel. This was they just studied the solitons with vorticity 1. So you see that it's fat because this is a distribution of the intensity, and the small hole in the center is actually the hole which is drilled by the vorticity. So this is quite a broad soliton with a large norm, so it's definitely stable. And then it's not only stable, but they were able also to simulate collisions of such moving solitons, and in addition to being stable, they also collide quasi-elastically, as it's shown here. Okay, now what about the experimental realization of such solitons? As I mentioned, there are optical media which are sufficiently accurately modeled by this equation. So experimentally, what was demonstrated in full detail, this is the stability of fundamental two-dimensional solitons of this type in this work by people from Brazil and France. But what is actually a more challenging experimental problem is to experimentally observe stability of two-dimensional solitons with embedded vorticity. Actually, thus far, it was not demonstrated in a fully relevant form. What was demonstrated in this experimental work was a partial solution of the stability problem for the soliton with vorticity, namely, so this is a side view. Actually, this is a vortex ring. This is an experimentally created soliton with embedded vorticity. So here, this is pictures when its power was low. Therefore, it's just a linear self-stretching, linear diffraction of the input, nothing else. It's a purely linear dynamics. Here, the power was larger, therefore originally the nonlinearity plays an essential role, and this vortex solitons was able to survive the propagation, which is roughly speaking equal to 5 characteristic diffraction lengths, so-called Rayleigh lengths. But then the dissipation, there is a dissipation in this medium. The dissipation it's actually nonlinear dissipation, which is represented by the so-called two-photon absorption, as this dissipation actually starts to eat the power of the soliton, and therefore it actually switches to the quasi-linear behavior, and then it loses its integrity, loses its self-supported shape, and starts to demonstrate the linear diffraction. So stability was demonstrated as a transient effect here of the vortex soliton. Now, another challenge is to try to at least theoretically to create such a soliton, stable soliton with embedded vorticity, but in the three-dimensional form. It was thus far there was no experimental result in this direction, but there is one theoretical result which was obtained already 20 years ago, and it was shown that indeed, if we look at this three-dimensional nonlinear Schrödinger equation with the competing cubic quintic nonlinearities, exactly solutions with embedded vorticity 1, part of these solutions may be stable. Roughly speaking, the criterion is similar to what I mentioned. They become stable if the norm is large enough, they become fat enough. And this is a direct numerical demonstration of the stability. So in that case, the shape of this solid three-dimensional soliton with embedded vorticity, it will be such a donut, or in other words, vortex torus, with a natural feature in the form of the central hole drilled by the vorticity. So here, one can take this numerically found stationary soliton and deliberately apply a relatively strong random perturbation. And so as a result of the evolution, it quickly performs self-healing and restores the stable unperturbed shape. But this stability was found only for embedded vorticity 1. For all such three-dimensional solitons with the embedded vorticity higher than 1, the result is that they are always unstable against spontaneous splitting. So this is some example. This is an example. For instance, we can take the stationary soliton predicted to be as a numerical solution with vorticity 2, and even without adding any perturbations, as the perturbation is created in direct simulations by small truncation errors of the numerical code, it quickly initiates the development of the instability, and in this case, the instability spontaneously splits this vortex torus or donut into 3 fragments. Each is, roughly speaking, a fundamental soliton, and this fundamental soliton is obviously stable because quintic self-repulsion does not allow the collapse to develop. Okay, now some more recent results. This is, now we can consider just the model only with the cubic nonlinearity, and it's possible to find a completely different mechanism of stabilization. This is related to the topic which recently, not very recently, but let's say in the course of the last 10 or 15 years became quite popular. This is a so-called emulation. So the experiments with Bose-Einstein condensates in atomic gases make it possible to emulate or simulate many effects which were previously known in much more complex form in the physics of condensed matter or in solid state. One of such effects is called the spin-orbit coupling. Spin-orbit coupling by itself, it is a very important effect in the physics of semiconductors. It means that when the electron is moving through the ionic lattice, due to the weak relativistic effect, the magnetic moment of the electron, in other words, its spin, starts to interact with the electrostatic field. Why it starts to interact with the electrostatic field? Because Lorentz transformation to the reference frame, which is moving along with the electron, it creates a small magnetic component out of the original electrostatic field of the ionic lattice. And so this weak relativistic effect actually gives rise to the coupling between the spin of the electron, in other words, its magnetic moment, and this effective magnetic field generated by the Lorentz transformation. And so this is what is called the spin-orbit coupling. So in the case of Bose-Einstein condensates, the physics is completely different. But what people were able to do, they were able to demonstrate experimentally that one can create a 2-component binary condensate with 2 components, and then, formally speaking, 2 spinor components of the wave function of electrons. Also, of course, electrons in the semiconductor are fermions, while this 2-component gas is a gas of bosons. Nevertheless, one can formally map 2 components of the excuse me, 2 components of the spinor wave function of the wave of electrons into 2 components of this binary condensate, and then it's possible to demonstrate the Hamiltonian of this bosonic gas will be essentially the same as the Hamiltonian which accounts for the spin-orbit coupling. This is a so-called Rashba Hamiltonian or Dresselhaus. There are 2 forms of them in semiconductors. Both of them can be actually emulated by means of Bose-Einstein condensates. So this formal similarity between the Hamiltonians makes it possible to effectively emulate the dynamics of spin orbit coupling in Bose-Einstein condensates, which is much easier than to observe this in the very complex form in semiconductors. And then it was demonstrated that, in particular, in 2 dimensions, all this can be represented by a system of 2 coupled nonlinear Schrödinger. In that case, it's usually called Gross-Pitayevsky equations. So this is a model for the 2-component condensate. Phi plus and phi minus are 2 complex wave functions of the 2 components. So here you can recognize as the nonlinear Schrödinger equation, a Gross-Pitayevsky equation with a self-attraction. Here, as I mentioned, the effect of the Feshbach resonance makes it possible to induce the effectively self-attractive nonlinearity in the condensate. And then these are the terms which represent the linear mixing between the 2 components, between the 2 equations. So these are purely linear terms, but what is essential, the linear coupling is performed not by the fields themselves, but by their first spatial derivatives. So this particular combination of the spatial derivatives was derived in earlier works as a manifestation of the spin orbit coupling in the form of the Rashba Hamiltonian. So after some derivation, one arrives at this system of 2 coupled Gross-Pitayevsky equations. So before this analysis, it was believed that if we have any kind of the model which combines the 2-dimensional nonlinearity and cubic self-attraction, no matter what, we will always have instability of solitons because of the possibility of the collapse. Now we will see a completely different result. So this possibility was analyzed in these works. Thus far, only theoretically, there was no experiment. So the 2-dimensional spin orbit coupling in Bose-Einstein condensates was observed, but thus far only in the linear regime, as a matter of fact. And then what one can do, one can look for stationary solutions to these coupled equations, and then looking at the limitations which is imposed, by the conditions which is imposed by this specific form of the linear mixing between the 2 components, one can easily see that the following ansatz is compatible with the equations. One can look for solutions when in one component it's just a fundamental soliton without any vorticity. But automatically the second component must be one in which we should assume vorticity 1. So exactly this ansatz is compatible with the structure of this binary Bose-Einstein condensate with the Rashba type of the spin orbit coupling. So here vorticity is +1 in this component and 0 in the first component. And then one can substitute the ansatz, obtain the system of coupled equations for these radial amplitudes, and then it's possible to solve them numerically or also analytically, approximately by means of the variational approximation. And then, indeed, this system produces a soliton. So this is a soliton which is illustrated by the radial structure of the 2 components. The red curve is a component with a 0 vorticity. Because it has 0 vorticity, it has a maximum at the center. And the dashed curve is the radial structure, the absolute value of the radial structure of the vertical component, and therefore, quite naturally, it has a hole in the center, as any vertical structure should have. And so this is a stationary soliton, and then the most important result is represents the entire family of such solutions. Now they depend on the arbitrary chemical potential mu, which should be negative. And what is shown here is the dependence between, this is maybe it's not seen, but this is this axis is actually the norm of the solution. This is the chemical potential. Now, what we see here, when the chemical potential is approaching -infinity, this norm will attain the asymptotic value, which is exactly that value of the universal norm for the town solitons. So in this limit, when mu becomes -infinity, this 2-component soliton will degenerate into a single component in which only the non-zero, all the norm will be concentrated in the non-zero, in the zero vorticity component, and the vortex component will become empty. However, at any finite negative values of mu, we have both components, and as you see here, the norm is always smaller than that critical value. What it implies, the total norm is always smaller than the critical norm, which is necessary to initiate the collapse. Therefore, this soliton cannot start collapse. It simply does not have enough norm, and therefore, as a matter of fact, all the solitons have nothing else to do but to become stable. Indeed, they are stable solutions. And by the way, they said we see that the slope of this dependence between the norm and the chemical potential is negative. Why this is an important fact? There is a famous necessary stability condition for any family of solitons in any dimension with any nonlinearity, which is supported by any kind of self-attraction. This is a famous Vahitov-Kolokov stability criterion, which was discovered by these people in Russia very long ago. And it tells the following: not sufficient, but the necessary stability condition for the family of solitons is that the slope of this dependence must be negative. Indeed, this condition is satisfied by this family, but it's not only, it's actually completely stable. And moreover, actually, it can be demonstrated not completely rigorously, but it's quite plausible that actually these solutions produce the ground state of the system. In the absence of the stabilizing factors, the spin-orbit coupling, the two-dimensional nonlinear Schrodinger equation with a self-attractive cubic nonlinearity does not have the ground state, or formally speaking, the ground state is a collapsing state, which is blowing up. Now we can actually restore the previously missing, well-defined ground state. And now another possibility, though the previous model just by definition had only nonlinear self-interaction, but no cross-interaction between the two components. The cross-interaction can be also introduced. It's possible to have the cross-interaction as well, depending on parameters of this binary condensate with some coefficient gamma. And now the result is that if this relative strength of the cross-interaction remains smaller than 1, which means that still the self-interaction is dominant, we will have, roughly speaking, similar stable solutions, and those solutions are called semi-vortices. Why semi-vortices? Because we have vorticity in one component and zero vorticity in the other component. Now, if gamma is present, we may have another solution. This solution is called the mixed mode. The mixed mode is a solution which actually mixes zero vorticity term and terms with vorticity in both components. Actually, this is not an exact answer. It's not exactly compatible with the equation. It's just the input which can generate some new solutions, or it can be used also for the variational approximation. So here we assume that we have approximately vorticity, the term with vorticity -1 in one component, +1 in the other component. This is a numerical solution, the radial structure. Now this complex form is the result of the fact that each component is a mixture of the zero vorticity and vortical terms, and also there is splitting between the two components due to the fact that vorticity has opposite signs in them. And so the result is that this is a family of such mixed modes, mixed solitons of mixed modes, and it can also form a stable family. But what is essential? This parameter gamma. As long as gamma is smaller than 1, we have, in principle, both semi-vortices and mixed modes, but only semi-vortices are stable solution. Mixed modes are unstable. However, if we have gamma larger than 1, they exactly switch the roles. Now, the semi-vortices still exist, but become unstable. And now, when the cross-interaction is a dominant nonlinear factor, in that case, the mixed mode becomes stable. This can be explained by the following fact. One can write the energy or Hamiltonian of this two-component system, and then one can calculate, one can fix the total norm, and the fixed norm, one can calculate the energy as here is, maybe it's not seen, it's the coefficient gamma. One can calculate this energy as a function of gamma. So what happens when gamma is smaller than 1, this branch which corresponds to semi-vortices realizes the minimum of the energy, in other words, the ground state, it's stable, and the mixed mode has high energy, is an excited state which is unstable. But when we pass gamma equal to 1, these two curves cross, and then at gamma larger than 1, the ground state, the minimum of energy, is provided by the mixed mode, it is now stable, it realizes a ground state, and the semi-vortices still exist, but now they're excited states which are actually unstable. Now, what about 3 dimensions? In 3 dimensions, it's possible to consider a similar model. It's not exactly the same. RUSA is a so-called Weil type of the spin-orbit coupling, but quite similar to what we discussed before. Here, nabla is simply the gradient operator. Sigma is this is a 2-component equation where sigma is simply the vector of 3 standard Pauli matrices. So this is some version of the spin-orbit coupling, similar to what we discussed before. Again, we may have both self-attraction and cross-attraction as considered the nonlinear part of this system. And again, it's possible to predict something using the energy of the system, and developing a simple variational analysis, one can predict that if the strength of the spin-orbit coupling is neither too large here, nor too small, one cannot prevent the collapse. So here we still have the curve of the energy, which goes to -infinity. But it's possible to predict the shallow local minimum of energy, and it may correspond to metastable solitons, which are not stable against very strong perturbations, which can provoke the collapse, but they can be stable against finite or small perturbations. Indeed, it can be demonstrated experimentally that they are stable against, not experimentally, numerically, of course, but they are stable against small perturbations. This is a typical shape of 2 components. This is 0 vorticity component, and this is a vertical component of the 3-dimensional metastable soliton in the form of a semi-vortex when this coefficient eta instead of gamma is smaller than 1. And this is its counterpart, is this bizarre form, is a shape of this metastable soliton of the mixed mode type. Also, 2 components are shown. The shape is such a complex because of because we have the mixture of 0 vorticity and vertical components in each wave function. And now we have maybe still something like 15 minutes or so, and let us discuss the last topic. The last topic is something which was developed starting in 2015, first as a theoretical prediction, and then, quite surprisingly, this theoretical prediction was really quickly realized in the direct physical experiment. So this is a possibility to stabilize soliton-like 3-dimensional objects in the 2-component Bose-Einstein condensate, to stabilize them against the collapse, and this way to produce stable 3-dimensional soliton-like objects. So this story started long ago. In 1957, a classical paper was published by Li, Huang, and Yang. Li and Yang, they are very famous theorists who were awarded with a Nobel Prize for the prediction of the parity non-conservation violation in weak interactions between elementary particles. In this work, they considered actually the corrections produced by the excitation of the so-called Bogoliubov modes, in other words, quantum fluctuations in the Bose-Einstein condensate. In the lowest approximation, the Bose-Einstein condensates can be quite accurately described by what is called the mean field approximation. Mean field essentially is semi-classical approximation. And so what was done in this old paper, they calculated the correction of the quantum fluctuations to the mean field. And then in 2015, a new step forward was made by Russian physicist Dmitry Petrov, who is a professor in Paris, and he actually wrote this Li Huang Yang correction as correction to the nonlinear Schrödinger or Gross-Petoyevsky equations for the Bose-Einstein condensate, and he was able to find a specific configuration in which this quantum correction is able to completely suppress the instability against the collapse and predict something very stable. So there was also an important paper by Petrov with another Russian physicist who is a professor in Barcelona, Grigory Astrokharchik. It was actually the similar analysis, but in the two-dimensional space instead of 3 dimensions. Okay, now this equation is an important result which was derived by Prof in 2015. So the first 3 terms, as we see here, is a traditional nonlinear Schrödinger equation with the cubic self-attraction. This red term is the correction, which is produced by the Li-Huang-Yang effect of quantum fluctuations around the mean field state. Now, its term seems a little bit strange because it's non-analytic. Non-analytic in the sense that it contains not the odd power of the absolute value. So in other words, the half integer power of the density. Nevertheless, it is a correct term, and coefficient gamma is positive. How it's actually derived? What one can do, so by itself, the Li-Huang-Yang correction can be derived only when in the given component of the condensate we have repulsive interactions. And of course, to produce something like a soliton, we need an attraction. And the approach developed by Prof is built as follows. One should take a 2-component condensate. Now, in each component, one has a natural self-repulsion, and then one has this Li-Huang-Yang correction to it. But applying the Feshbach resonance, what one can do, one can keep the self-attractive interaction in each component, but simultaneously induce effective attraction between the 2 components. Then, at least for simplicity, one can consider the symmetric configuration when the wave functions of 2 components are exactly equal to each other. Then instead of 2 nonlinear Schrödinger equations, we have essentially a single equation. Then there will be competition between natural cubic self-repulsion in each component and also cubic attraction between the 2 components. Then one can choose the parameter regime in which the attraction between the component is slightly stronger, so effectively one will have in the single equation the sign, the cubic term with the sign which corresponds to self-attraction, and then one still inherits from the 2 components structure of this system, one still inherits the quartic self-repulsive term. Now, what is immediately obvious, in this equation, we will have no collapse, because when collapse is going to occur, the local amplitude will become large. It means that then this term will become eventually dominant. It will arrest the development of the collapse and will stabilize whatever we have there. So therefore, it's immediately obvious that fundamental states with zero vorticity should be stabilized. Actually, people usually do not call these objects solitons. They prefer to call them quantum droplets. The reason why they are called quantum droplets is that if we try to construct such a solution, we can again try to find the stationary solution. First of all, in the 3-dimensional case, in the spherically isotropic form with just some real function capital phi of R, for which one needs just to solve this radial ordinary differential equation. And now we have the competition between cubic and quartic terms with opposite signs. And then this elementary analysis demonstrates that the squared local amplitude of the solution can never exceed this maximum value. Actually, we saw a very similar property in the case of the cubic quintic nonlinearity. I mentioned it here. There's a similar property which is produced by the competition between cubic and quartic terms. And then if we want to create a solution with a large norm, we cannot exceed this local maximum. So what the system does, it creates very fat soliton with a very large width, but with a limited local amplitude. Therefore, actually, this means that this quantum gas has a property, because the density cannot exceed the particular maximum. Essentially, one can say that this is an incompressible quantum state of matter. An incompressible state of matter is usually called a fluid. Therefore, this is considered as a quantum fluid. Actually, this is a quantum fluid which is, its density is actually smaller than the density of air, of normal gas, maybe by 3 orders of magnitude. Nevertheless, it's actually essentially is a quantum fluid, actually the most dilute quantum fluid which is known in nature. Therefore, particular stable localized objects which are produced by this fluid are called droplets. So this example of such solution, so in the spherically symmetric state, first, if the norm is not very large, the radial structure is still soliton-like here, or sometimes it may be called Gaussian-like, but it's sufficiently localized. But if we want to create a similar state with a large value of the norm, as I mentioned, the density cannot exceed the particular maximum, therefore it becomes very broad. And this is what actually, essentially, this is what people called a quantum droplet, and it's predicted to be stable. So experimentally, it was quite quickly realized using this two-component condensate. It was a mixture of two different hyperfine states of the atom of potassium-39. The number of atoms in the experiment was, roughly speaking, 10,000. And in this first experiment, which was performed by the group of Leticia Teruel in Barcelona, actually, this was a stable quantum droplet. So what happens here? Here, actually, the density is not sufficiently large, therefore it suffers just the decay. Here, the density is too large, and due to the attraction, self-attraction is too strong, it means it's killed by the explosion, by the collapse. But if the effective strength of the nonlinearity is appropriate, then they observe an effectively stable droplet. This droplet is essentially a quasi-two-dimensional object because in the third direction, it's still its shape and stability was supported externally by the trapping potential. But then the experiment using the same atomic species was reported by another group of Massimo Inguscio from Florence, and they actually were able to demonstrate the completely spherically symmetric three-dimensional droplet. So again, here the nonlinearity is not strong enough, therefore it decays, but here the nonlinearity has a correct value, and therefore it forms an effectively stable three-dimensional, this time completely isotropic, truly three-dimensional quantum droplet. Then, as concerns the theoretical development, thus far, no one tried to create, to experimentally embed the vorticity into this droplet, but it's at least quite interesting to analyze theoretically if such a droplet will be also stable when it carries the vorticity. So first of all, in the two-dimensional version, it was done in this work, and the result is indeed, it's quite possible to predict such stable droplets in principle, with more or less with any value of the vorticity. Here it was done explicitly for vorticity up to 5. So this is the top view of such a two-dimensional object with embedded vorticity. So this is vorticity 1, vorticity 2, 3, 4. So these three vortex solitons are stable. This one is unstable. So these are their cross sections, radial structures. If it is unstable, it splits. And then the necessary condition for first of all, for the existence of such a droplet with embedded vorticity is that this is a norm. The norm should exceed a particular minimum value. This is vorticity S. But if we want to make it stable, the norm should be still larger. So only if the norm exceeds this threshold value, then above it, such droplets with embedded vorticity become stable objects. Then a really challenging possibility is to predict this in the fully three-dimensional form, because the previous analysis was two-dimensional. And indeed, it was demonstrated. For example, here, what happens? One can create as a three-dimensional vortex torus. This is a vortex droplet with embedded vorticity 1. You see it's broad here. Right? If it is not sufficiently broad, or in other words, if the internal inner hole is not very narrow, in comparison with the overall size, it's still unstable. For instance, here it spontaneously splits into 3 fragments. Each fragment will become a stable fundamental droplet. Nevertheless, if we really pump a sufficiently large norm into this object so that the relative size of the inner hole becomes small enough, we can predict a stable, fully three-dimensional vortex torus, in other words, the donut with vorticity 1, also numerically found were examples, at least, of such objects with vorticity 2. Okay, so there is some relatively recent review on this topic. And now conclusions. So the conclusions are that there is a long-standing problem of the instability of multidimensional solitons. A relatively old solution was proposed in the form of the models with the competing nonlinearity, for example, cubic quintic. And more recently, completely new solutions were proposed. The theoretical one, it was the use of the spin-orbit coupling, in which case it's predicted that one can do something which was considered previously to be absolutely impossible, namely completely stable two-dimensional solitons, which I described essentially by the cubic nonlinear Schrodinger equation, two-component equations. They can be made completely stable, can create actually ground state by means of the linear spin-orbit coupling. And then the most recent achievement, which was very exciting because it was also realized experimentally, is the possibility to use the quantum correction, the Li-Huang-Yang effect, as a quantum correction added to the mean field approximation, and it predicts stable soliton-like objects, completely fully three-dimensional soliton-like objects, which people call quantum droplets, in the two-component Bose-Einstein condensate, and this was indeed produced experimentally, also thus far without vorticity. Also, theoretically, the stability with vorticity was also predicted. And then, as concerns the possibility for further developments, of course, it's actually, as we could see here, is it usually happens, the experiment is lagging far behind the theory. So it's a very relevant problem would be to push ahead the experimental studies. For example, in the case of the quantum droplets, it would be very interesting to create such droplets with embedded vorticity. So thus far, the experimentalists, when they asked if they can embed vorticity into the quantum droplets, they would say something like, well, it's a very challenging experimental problem. Why it's very challenging, I'm not sure, but this is what they say. And that concerns theory. There are also the directions to develop theory, in particular, because soliton with embedded vorticity is a topological object. So vorticity by itself is a topological charge. It's possible to develop more sophisticated models in which it will be, one can create the more complex localized objects, not roughly speaking, not with one, but with two independent topological charges. Usually for this, one needs to have a multi-component system. And this way one can create, for example, famous skyrmions, and also one can create hopfions. So hopfion is an object like this. It's actually, roughly speaking, the vortex torus, so the three-dimensional solitons with embedded vorticity, which we discussed already, but here it carries an additional quantum number, additional topological charge. This actually, its toroidal core itself can have intrinsic twist. It can be subjected to the intrinsic twist, and then one will have this hopfion, which carries two independent topological numbers, the overall vorticity, as before, and in addition to this intrinsic twist. And so it was demonstrated using some particular model, actually one component, but with some effective nonlinear potential. I don't have time to talk about it in detail, but it was possible to find solutions when, in the case when both the vorticity takes values plus or minus 1 and the intrinsic twist, this internal quantum number also takes values plus or minus 1. It is possible to have stable hopfions of this type. They are called hopfions because objects with such topological properties were first, in the abstract form, they were theoretically analyzed by the German mathematician Hopf. So in most cases, actually, they are unstable, but nevertheless, some stable hopfions in this model can be found too. But actually, we don't have much time to talk about this model in detail. And okay, so I guess it's maybe relevant to stop here. So thank you very much for your interest in this talk. And actually, of course, copies of this of this talk are definitely available for distribution. Thank you.
Thank you, Professor. Thank you. So now the forum is open for questions, clarifications, doubts.
Yeah.
So, thank you very much, Professor Malomed, for a very beautiful lecture on multidimensional solitons. So, I have a couple of questions or remarks. If you consider two-dimensional nonlinear Schrodinger equation, for example, it's possible to find exponentially localized solutions by introducing additional scalar potentials, as in the case of Davis-Stewardson equation. So you
Well,
can
if you do, okay.
Davis-Stewardson equation, so you can get analytic forms of two-dimensional soliton equations, exponentially localized. So you can use a Veclan transformation or in inverse scattering or even Hirota bilinearization. You can get exact solution. But the nonlinear Schrodinger equation in two dimensions is modified with the addition of a scalar potential. So it is possible from a different point of view to modify the nonlinear Schrodinger equation suitably, at least in two spatial dimensions, to get exact analytic solutions, and you can study their collision properties.
Yeah.
I do not know whether this can be extended to three dimensions, but at least in two dimensions, you can study exact localized solutions, exponentially localized solutions. So do you have any remarks on these kind of possibilities?
Yes, I can say something about this. Indeed, this work was done. So what was done, people considered both two- and three-dimensional nonlinear Schrodinger equation with this cubic self-attraction and with additional confining potential. So the potential was a harmonic oscillator trap, so quadratic potential. And what was considered in detail a stability of two- and three-dimensional solitons, which are embedded into this potential. And in particular, what was especially interesting to analyze the possibility to stabilize such solitons with embedded vorticity. And the result is roughly speaking as follows. All fundamental solitons with zero vorticity, they are completely stabilized by this trapping potential, both in two dimensions and three dimensions. They're complete. No, in three dimensions, they're strictly speaking not completely stabilized. There are two branches of the solutions, but one of them is completely stabilized. In two dimensions, all fundamental solitons are completely stabilized. Now, quite a non-trivial situation was found for soliton with embedded vorticity, namely, in both two and three dimensions, it was found that a part of the family of solitons with vorticity 1 is stable. Only part of it. Actually, it is possible easily to demonstrate that then there is a family of solitons with vorticity which completely satisfies the Vahitov-Kolokov stability criterion. But nevertheless, in that case, it's really not sufficient. It's only necessary. Because Vahitov-Kolokov, roughly speaking, it only predicts the stability against the collapse. It doesn't know anything about the possibility to have the instability against spontaneous splitting of the vortex soliton. And it was found that a part of the family of solitons with embedded vorticity 1, they are stabilized by this external potential both in two- and three-dimensional cases. According to the results which are known to me, all solitons with vorticity 2 or higher, they remain completely unstable in this case against splitting.
Yeah, but the kind of potential I have in mind is they have a coupled partial differential equation, but they do not evolve. So, for example, in the Davis-Stewardson case, so you have the potential which has the equation pi xx plus pi y equal to mod q square of xx or something like that. So that is coupled to the two-dimensional nonlinear Schrodinger equation. In that case, the system admits exact localized solutions, Romayan-like solutions. So there is a possibility of considering more general form of potential, and so that the energy is supplied all the time from outside through this potential to the system, so that you get stable localized structures. So that is
in the case of Davis-Stewardson, you definitely have two-dimensional solitons. Also, you have stable two-dimensional solitons in the case of KP1, atoms of Petriashvili of the first type. This is the so-called lumps. But at least in what I remember exactly, in the case of atoms of Petriashvili of the first type, you don't have, there are no vortex solutions, only because this is a real wave field. In the case of Davis-Stewardson, it's complex. if there are exact solutions with the vorticity, at this moment I don't remember, but I guess they are not known.
Yeah. The second question I would like to point out is recently with Safik Ali and Govindarajan, we have pointed out that negative index materials, metamaterials, they can admit stable light bullets. And even under collision, I mean, they can undergo collision and they can come out without change of form or, without change of form. So elastic collision. So do you have any comments on the possibility of collision, having collisions which is elastic like?
Yes, okay.
I mentioned. Yes.
Okay, so I mentioned when I talked about the experimental realization of the quantum droplets, I mentioned that there were two experiments. One was performed in Barcelona by the group of Letizia Torrell, and the other one in Florence in Italy by the group of Massimo Inguscio. So in the group of Inguscio published at least two papers. So first paper is one which I mentioned, where they reported the creation of stable quantum droplets, which had actually a fully isotropic three-dimensional structure. Now, they had, soon after that, they had another experimental paper. In that paper, they exactly studied experimentally collisions between such stable quantum droplets, and they demonstrated that in most cases, they collide quasi-elastically.
Okay.
And of course, this can be also in the framework of this equation of Petrov, which I mentioned. This is the equation with the cubic quartic nonlinearity. It's not very difficult to simulate such collisions numerically. And if I remember correctly, in most cases, the collisions seem quasi-elastic, but maybe in some cases, they can also merge because because these are essentially droplets of the quantum fluid. So you can imagine that if you collide them slowly, two droplets can readily merge into a single droplet. So this may be observed as well. But if you collide two droplets fast enough, they will simply bounce back from each other.
Okay. Okay, thank you very much. Thank you.
Professor, are you able to read the chat box?
Yeah, I will try to see. So this is more options. Okay, so this is, okay, where is the chat? Okay, yes, I see. Okay, let me go to the beginning. Oh, there are many questions. Okay, so this is a question from Prashant Singh. Why 2D stable one soliton couldn't be obtained for NLS with cubic self-attracting nonlinearity by reducing the nonlinearity coefficient to avoid singularity? Instead, it can be avoided by the presence of quintic. Okay, by reducing just by making if I understand the question correctly, this question, if you make the cubic coefficient smaller, but still you don't change the sign. Of course, you can reverse the sign, but then you will have no solitons. There will be no self-attraction. If you even make it small, essentially this will be exactly the same situation because you can apply the scaling. By means of scaling, you can always actually, even if physically it's a small coefficient, you can rescale it and the effective equation will always have the same size of the coefficient. So the situation will be the same. If you just make it smaller, you will not stabilize the solitons unless you introduce something new, some new element. A new element may be this quintic nonlinearity, for example, or spin orbit coupling. Okay, then there is another question from the same participant. Even though mathematically it comes, but I don't get any physical intuition, that why the presence of an extra dimension increases the effect of cubic nonlinearity, such that the soliton approaches singularity. Okay, so in very intuitive physical terms, it's indeed maybe difficult to demonstrate, but nevertheless, it's not very difficult to understand because, well, I would say in a few words, it's necessary actually it's possible to explain it in detail, but this will take time and it will be necessary to write some equations. But essentially, what one can do, one can write just the Hamiltonian or energy of this multidimensional nonlinear Schrodinger equation, actually with an arbitrary degree of the nonlinearity. Just you can analyze a general case. And then you can, in the Hamiltonian, essentially you have two terms. One term is the gradient energy, which actually represent essentially diffraction or dispersion, and which tries actually to stretch the wave field that tries to drive the decay of any localized object. It's a because it generates the linear terms, the linear dispersion and diffraction as equation. The other term is the term which accounts for the nonlinear self-interaction. So it will be, so the gradient terms is positive because it's actually the system tries to minimize it by self-stretching, and the terms which accounts for the nonlinear interaction is negative, and because it's negative, the system really tries to make it to minimize it by making the amplitudes larger and larger, because then the terms will grow to minus infinity, roughly speaking. This is a development of the collapse of the singularity. And now what you can do, you can say, okay, let us fix the norm, because the norm is conserved, the total number of atoms, for example, in BEC, or the number of photons is optical signal, it's fixed. And then let us try to compare these two terms of the energy in different configurations. We just introduce some characteristic size of this localized object. So you can consider the limit when the size is going to zero, so this localized object is trying to compress itself. So if collapse means that the size will go to zero, and then if in this limit, when the size is going to zero, you should look at the behavior of the two terms. One goes to plus infinity. This is a repulsive term, the gradient term, and the other goes to minus infinity. This is self-attraction term. And you can ask the question, which term will be both dominant, but you don't know in advance before the analysis which one will grow faster. And here you will obtain the result. Namely, if you take, for example, the cubic nonlinearity in the three-dimensional space, you will see that for any fixed value of the norm, asymptotically in this limit, the term which corresponds to the cubic nonlinearity always dominates, and the system will inevitably start the collapse. On the other hand, in the one-dimensional case, you see that the gradient term will always be dominant, which means that the soliton will always be stabilized because the collapse will have no possibility to occur. And in the critical case, two-dimensional, you will see that both terms, they have the same type of the singular behavior. And therefore, which one dominates depends on the relative coefficients in them. And the relative coefficient is determined by the norm. So because the term which accounts for the nonlinearity, it obviously has a higher power of the nonlinearity in this coefficient than the norm, which represents the linear terms. And therefore, you will arrive at the conclusion. When the norm is large enough, the term which is going to minus infinity, which represents the self-attraction, it will be dominating, and therefore the collapse will occur. On the other hand, if the norm is smaller, then the dominant term will be the gradient one, which will formally approach plus infinity, and it will prevent the collapse, and instead your input will decay, but it will not be collapsing. So this way it's possible to arrive at the conclusion in a more or less physically transparent form. It's not immediately, so to say, intuitive, but nevertheless it's sufficiently intuitive after this analysis. By the way, this approach has a particular name. It's called the key word for this analysis is virial. It's called the virial approach or virial consideration. Okay, yeah, there is another question. Yeah. Again, from the same participant. Is there some way to find the flow of effect of nonlinearity in different dimensions? Would it flow symmetrically? Flow, I'm not sure what is meant by flow. Yeah, maybe, well, it's if it is an additional term of the equation, or, well, I'm not sure how to answer this question because I'm not sure exactly what flow is meant. So maybe I will not try to guess. And let us look at the next question. This is again about the flow. Maybe it will be clearer here. If it flows symmetrically, then why the effect is unable to get balanced by the dispersive effect, which is present by the same magnitude in the x and y direction in the equation itself? If it does not flow symmetrically, then so symmetric. I am not sure again about the exact meaning of the question. Maybe by the symmetric flow, what is meant is that, for example, if you have the two-dimensional case, if the solution remains axially symmetric, or in three-dimensional, if it remains spherically symmetric. But actually then, this analysis, which I mentioned right now, such as a virial analysis, it actually definitely assumes that we do not break this natural cylindrical or spherical symmetry. So I don't think that this consideration will essentially change the situation. Actually, another question, which I'm not sure if it's related to this or not, can be asked. For example, if we have a a soliton, for example, in the two-dimensional, if we have the soliton with axial symmetry, if it will be stable or not against the deformations which breaks the axial symmetry, and this will actually lead us to the very important issue which I tried to discuss in this talk, namely, if it is a fundamental soliton with zero vorticity, it's always stable against such a perturbation. But if it is a vortex soliton in the form of the vortex ring, a crucially important possibility is that it may be unstable exactly against this perturbation, and this perturbation can spontaneously break the axial symmetry and split the vortex ring into fragments. Okay, this is how I can understand the question. Now, there is the last question from Govindaran Arjunan. All of the theoretical models were stabilized in an ideal setting without taking into account the role of intrinsic loss. So what happens to the stabilization of higher order localized modes if the impact of loss is considered? Okay, in contrast to the problem solved by direct analytical methods, this can indeed be done easily, as most of the works deal with a numerical study. Okay, does it have a significant impact? Yeah, okay. So definitely there are models which easily predict stable dissipative solitons in multidimensional cases. And in that case, what is necessary to do is necessary again to play games with different nonlinear terms, this time dissipative terms, both linear and nonlinear. So here, the main point is that, first of all, because this is a dissipative equation, we may have, first of all, linear dissipative term. The linear dissipative term must correspond exactly to dissipation and not to gain, not to anti-dissipation. Because otherwise, if we have any localized state, it doesn't even one-dimensional, and we have still the linear gain, such a fundamental soliton may formally exist, in particular in the one-dimensional cubic equation. Is called, in that case, the complex Ginzburg-Landau equation. There is an exact solution for this case. It's called usually the Leonard, it's called the Stanflo, the first, I forgot the name, the first name, Stanflo and soliton, which was discovered by Stanflo and his co-author. Somehow I forgot at this moment the first name. But these solitons are unstable because if you have definitely unstable if you have the linear gain. Now, to have just a stable zero background around the soliton, you need to have in the dissipative system linear dissipation, but you must support something. With pure dissipation, you will have nothing. So you must also, to have the dissipation, to have the possibility to support something, you need to apply the nonlinear gain. And the simplest possibility is to apply the cubic gain. In optics, it's actually possible experimentally by means of what is called saturable absorption. But then if you have the competition between linear loss and cubic gain, everything will blow up, of course. To stabilize everything globally, on top of it, all you need still to apply the quintic gain. So then you have the following competition: linear loss, cubic gain, and quintic loss. And then on top of this, of course, you may have also conservative nonlinear terms. Or cubic or quintic, it's not very important, as a matter of fact. And then, as a result of all these games, you will be able to predict stable multidimensional dissipative solitons. And moreover, in some cases, you can predict such dissipative solitons with embedded vorticity, and they will have a chance, in some cases, to be stable even when the vorticity is present, even in the three-dimensional situations. There were works which demonstrated theoretically that such dissipative solitons with a cubic quintic nonlinearity and with embedded vorticity, even this object may be stable. So indeed, such stable multidimensional solitons are possible. They are considered, so the analysis is very different from what I tried to outline here for conservative solitons, but okay, there are many results on this topic. Actually, in the introductory part of this talk, I mentioned some particular review, which is recent review, which is focused exactly on multidimensional dissipative solitons.
So, is there any other question?
Yeah, something else appears. I see. Okay, again, Prussian thing. Sir, by symmetrically, I mean the effect is homogeneous in XYT space for 2D solid homogeneous. But well, okay, you know, it's necessary to discuss it somehow separately, because to tell the truth, I at this moment I don't want to guess what is the exact meaning of this question, because I'm not sure. It's maybe necessary to discuss it separately. I'm sorry, but because I don't understand the exact meaning of the question, I cannot give a definite answer.
So, Prasad, do you have any other questions? Do you need more clarifications? We can email to Professor Malomed.
Yes, of course. If someone wants to have to discuss in more detail, it's possible to send by email. I will, if I will be able to understand and respond, I will try to respond.
Are there more clarifications? Okay. So there are no more questions, Professor. So in that case, I would like to conclude the session by thanking you for accepting our invitation and giving a wonderful talk on multidimensional solitons.
Okay, thank you very much for the invitation. It was my pleasure to have the chance to give this talk. Thank you.
Thank you, Professor. Thank you.